Good evening, everyone. Thank you for joining us for today's meeting. This is the first virtual session hosted by the South Florida chapter of the Vertical Flight Society. We're joined today by members of local chapters of the AIAA, the Society of Flight Test Engineers, and the Society of Experimental Test Pilots. My name is Phil Aldridge, and I'm the president of the South Florida chapter of the VFS. I'm joined tonight by Randy Parsley from the AIAA, along with Lester Ingram and Gareth Roberts from the SFTE. For today's meeting, Christiaan Corey and Bill Fell will be talking about the future vertical lift, or VFL, at Sikorsky. Let's do a little housekeeping first. If you've got any questions during the presentation, then please type them in the question box in the GoToWebinar panel. I will see them, and then I'll be able to ask one of our presenters that question as it pops up. Just a reminder, this is probably the first and last meeting of the year because it's taken us so long to get this organized, and we've got holidays coming up. So look for another event in the new year. Although the Vertical Flight Society guys, we may have a Lichten Award audio conference before then, but look for us next year. So Christiaan Corey is an experimental test pilot at Sikorsky, which is a Lockheed Martin company. He joined Sikorsky in 2008, having spent 11 years as an officer in the United States Marine Corps, where he flew the 53E. Christiaan started his career at Sikorsky as a production test pilot, providing both production and training support in all of Sikorsky's military and commercial helicopters, while working as a project pilot on the 53K program. 2016, he attended the National Test Pilot School in Mojave, California, where he completed his performance and flying quality syllabus. Upon returning from this training, he began working as an experimental test pilot in support of numerous programs, primarily the 53K. In 2018, however, he joined the Future Vertical Lift program, where he supported both the S97 Raider and the SB-1 Defiant as a project pilot. He's the lead project pilot on Sikorsky's Future Attack and Reconnaissance Aircraft, FARA, otherwise known as the Raider X. Bill Fell has been actively involved in the forefront of most advanced rotary wing development programs for the past 20 years. As a Sikorsky experimental pilot, Bill's currently the lead pilot for the S97 Raider and the SB-1 Defiant, both X2 technology high-speed rotorcraft programs. Bill flew the first flights of both of these unique fly-by-wire rotorcraft. Prior to joining Sikorsky, Bill spent 20 years in the US Army, including 9 years as an experimental test pilot. Most notably, he was the only Army experimental pilot flying the two Comanche prototypes from 2001 to 2004. His experience in the Comanche included many rotorcraft firsts and demonstration flights. Today's presentation will be on Sikorsky's S97 Raider program. The S97 continues flight test efforts, breaking new ground and testing new technologies in support of the aforementioned FARA program. The 97 is a company-funded X2 technology aircraft that to date has flown approximately 90 hours and achieved well over 200 knots in level flight and angle of blank turns up to 60 degrees. The rigid rotor aircraft has a pusher propulsor to achieve higher speeds. The Raider is a slightly smaller version of Sikorsky's FARA offering to the US Army. Bill and Christiaan will provide an overview of the aircraft and discuss testing completed in the past and talk to some of the testing on the horizon. Over to you, Christiaan.
Well, Phil, thanks. What a kind introduction, and it's certainly our pleasure to be with you all this evening, though it be virtually. I suppose I'll start at least my bit of the pitch here with a breaking of the cardinal rule of public speaking, which is to begin one's speech or talk with an apology. But I'm new to the world of virtual speaking, and so I will just have to assume that you're all with rapt attention sitting on the edges of your seats, clinging to my every word. And with that confidence, we will muster through our quick talk here about where we intend to go in the future of vertical lift. The keepers of such things advise me that it is appropriate to post statements like this at the beginning of a presentation like this, particularly one where we find ourselves in contracts with the government and others. And so I have taken the wise step of including this legal disclaimer. I think I'm also inclined to say that something along the lines that the opinions or impressions that Bill and I offer this evening are more than likely our own. We may share them, however, Sikorsky nor Lockheed Martin necessarily does as well. So let's step to it. Phil talked about who we were, and there's probably no need to belabor that. I think most of you know us, and it's tough when you give a talk like this to an audience that you expect knows a lot about what you do. But I think the number one mistake we make is assuming that everyone knows what we know, and so hopefully we will at least broaden your aperture as to what's going on at Sikorsky in this little slice of the business. So I will step us through a little bit of the history of X2 technology, try to answer the question, why X2 in the first place, describe where we have been and where we are going. The latter bits, I think that will be Bill's bit of the talk to give. So our story starts with what might be considered humble beginnings, but I would offer that they were probably bolder in many ways than they are today. Pictured here is our founder as he makes the maiden voyage of the famous VS 300 on May the 20th, 1940. So some 80 years ago. Quite a bit has changed, not the least of which is the fact that we do not find ourselves donning fedoras as we go about our business, much less flying with coats and ties. But back in the day, I suppose that's how you went about it. I'm struck by the quote Mr. Sikorsky leaves us that, you know, at that time, the chief engineer was often also the chief test pilot as well, and that that had the fortunate result of eliminating poor engineering early in aviation. We have clearly diverged from that path where we leave the heavy engineering to the pros that have dedicated their lives' works to doing that. And Bill and I are fortunate enough to just ride on the coattails of the hard work that you all do day in and day out. But we've reimagined that future for sure, and in the present day we find ourselves flying machines such as the S97 Raider. I think it's safe to say that Mr. Sikorsky would look fondly on the advances that his company has made over these 80 years, and I think he would be equally enthusiastic about the future that we're looking forward to as well. But transformation's been a theme, and it wouldn't be a presentation given by former military pilots if there wasn't cool videos. My disclaimer when I show this video that the folks in marketing put together is that it is clearly a marketing video, and you'll pull some of that out of the text, and it is clearly a video that was made on the professional side of things, and this is to say that it is not set to an AC/DC song as any fine piece of video featuring flying machines in my mind should be. But without further ado, I will cue video and hope that the streaming is not too terrible. So without further ado, cue video.
Not to jump in, Chris, but one thing I know is remember now is that the audio doesn't come through. So if you could maybe put your earphones down next so we can hear it.
Oh, sure. Yeah, it's just some really profoundly dramatic music. You'd be better to listen to AC/DC.
Yeah, even that's not working very well. Sorry.
Pumpkins, ghosts.
All right. Well, hopefully that wasn't too laggy. It comes out fine on my computer, so one never knows. The story of X2 technology. Well, I suppose we start back in the late 1970s. So like a short 30 years after Mr. Sikorsky's first flights in the VS 300, we have proven that not only is the helicopter a viable means of transportation, but it has actually become, as we've seen in the Vietnam War, then fundamentally critical to the manner in which the United States military will carry out campaigns, both in that war and certainly wars throughout the future. So having proven the concept, I guess the next question is, how do you improve on the concept? And I expect at the time, as the Sikorsky sat around pondering that, they recognized that one of the limiting factors to how fast you could push a machine through the sky, as we all know, is the notion of retreating blade stall, and the fact that that you've got to somehow maintain equal lift on either sides of the rotor disc. And so in an effort to address that physical phenomena, I suppose they imagined, what if you just set two sets of rotor discs, one on top of the other, and spun them in opposite directions? In so doing, you would have the ability to ensure that there was equal lift present on either side of the rotor disc, and then you'd be able to get past the notion of retreating blade stall. The next question, I suppose, comes to, well, how do you thrust the machine through the sky and achieve the speeds? Because as you can imagine, when you place rotor discs in this kind of proximity, the ability for them to come into closer proximity or even touch one another is completely and utterly unacceptable. And so the rigidity required to achieve this technology suggests that you're not going to be able to fly it in the manner in which a traditional helicopter was flown. And so at the time, the approach that was chosen was to strap a couple of turbojets on either side of the fuselage and let her rip. And let her rip they did. They flew this thing out to 240 knots, faster still in a dive, and they proved that the concept was viable. But ultimately, it was a concept that wasn't quite ready for prime time. A couple of reasons feed into this. I mentioned the rigid rotor blades, and that has the pesky off-put of high vibrations through the fuselage, which I expect were deemed unacceptable early on, and that probably continued throughout. Additionally, high pilot workload. So it's a mechanical flight control system, and mind you, this is back before the days of digital engine controls. So I can only imagine one guy like Ringo Starr is trying to beat on the drums and the stick and rudder skills going. Meanwhile, the other fella is responsible for monitoring both NR as they go out into higher forward flight. But I suspect somebody's got to keep track of what those jet engines are doing. And the workload involved in those two things are probably just a bit more than is going to be marketable at the time. It turns out that that turbojets are not the most efficient way to thrust a rotary wing machine through the sky. So the prop efficiency, I think, was deemed probably less than optimal. And finally, the overall drag of the system, I think, could use improvement. So on the shelf goes the S69. We'll fast forward the movie until the early 2000s. We've witnessed the 9/11 attacks, and the world's gone off to war, and sensing the change of times. You'll recall at the time the Army were headed down the program of building the Comanche, what many would consider to be the finest flying machine that Sikorsky had ever built. But a decision was made that that was not probably the program for the time, and so that program came to an end, and the funds from that, to our betterment, I would offer, went into the production of Blackhawks and Apaches. And so that fuels the next several years of production at Sikorsky. But there's a couple of nuggets that come out of that experience, not the least of which I would offer is the fly-by-wire flight control system, and certainly some of the improvements in engine governing capability. And so I imagine in the early 2000s, folks realized that, you know, we had a technology and we had some limitations to it. And I bet we've got some solutions that we might apply to that old problem. And so we set about designing and building and flying the X2 technology demonstrator. She flew her first flight in 2008. You can see she was a svelte 6,000 pounds, a third the weight of the predecessor, 250 knots straight and level and 263 knots in a dive. I think personally the most impressive thing about the feat was the fact that these folks pulled this off in all of 17 flights and 17 flight hours from the hover to 250 knots. I would argue that that is nothing short of remarkable in and of itself. All in all, they flew 23 flights and logged just over 20 flight hours. Along the way, they managed to win themselves the 100th annual Collier Trophy in 2011. So where do you go from there? You've proven that the capability has potential, and so the next logical step is to try to package that capability into something that would actually be practically applicable. And along then is and so is born the S97 Raider program. Raider shown there in the rear next to the smaller and more svelte X2 technology demonstrator. As time goes on, though, we'll develop yet another of those X2 fly-in machines in a partnership with the Boeing company. We built the SB1 Defiant, another technology demonstrator, answering another question for the Army. And as I describe those questions, I'll show you the roadmap of how that all comes to pass. You can see in 2011 we conclude operating the X2 technology demonstrator, and that begets S97 Raider. And around about this time, you know, the Army is, and the DoD, I suppose, are playing around with this notion of future vertical lift and how are we going to state of the art. I would say, fortunately for us, certainly us who were involved in Sikorsky, we started that program, our forefathers started that program in the early 2000s, because you don't just, I think, wake up one day and decide, hey, we're going to transform the state of the art, but rather you do that step by step. So you can see where those two pathways diverge. You've got the FARA program that the Raider S97 would segue into, and then you can see Define as a feeder into the FLRAA program. So the Army are looking to replace the Kiowa Warrior kind of a mission down here on the FARA, Future Attack Reconnaissance Aircraft, and then in a larger category, the Future Long Range Assault Aircraft. Think about Black Hawk replacement here. And so these are really the two paths of the future, and what an exciting future it is. I would actually tell you it's here now. I'm sure we're all keenly aware that like teams are chosen as far as this goes. So in this corner, you'll have Sikorsky aircraft facing off against Bell helicopter as we build Raider X for us and the Invictus in the case of Bell helicopter. And on the other front, Sikorsky is teamed with the Boeing company to answer that medium lift long range mission, and again that's going to tee off against the Bell V280, the Valor. So that's that. So why X2 technology? I'll wrap it up with that. I think it's a worthy question. I suppose, like anything, if you're not evolving, you're dying. The same is true of business as it is of threats and the technology that try to defeat those threats. So I think it's right and it's incumbent on us to recognize the next war will be markedly different than the past. And if we don't have new solutions to new problems, then we are going to find ourselves at a significant disadvantage. I think we'd all agree that if I was going to sit down with a blank sheet of paper and design myself a brand new flying machine, I'd want it to be fast. I'd want it to be maneuverable. It'd be really nice if it went a long ways. And in the case of a fighting machine, survivability and lethality, if that's your game, are kind of nice to have too. But I think we need to be keenly aware of the bigger environment that we operate in, and that's where cost counts and sustainability. These aren't Fabergé eggs that we're building. These are fighting machines that we're going to send into challenging places, and we're going to ask them to do challenging things under inordinately difficult circumstances. We expect them to do them safely and reliably. And so that is something that you've got to think about when you build them in the first place. I talked a little bit about, X2 gets you the speed, but there's another great advantage, I would say, in the coaxial rotor system, and that's that it offers another solution to the problem that Igor Sikorsky himself had to address back in the early days, which was how do you solve for Mr. Newton's third law, where equal and opposite reactions occur based on the single main rotor, which would, if left unchecked, find the fuselage spinning wildly in the opposite direction. His approach, and I would argue that it has yet to be too well bested, given that 90 or 95% of modern day helicopters continue to incorporate a sideward thrusting tail rotor, was just that, to put a tail rotor on the machine. But as we all know, there's trade-offs to that. That tail rotor requires power that could ideally be more well served, propulsing the engine, giving you better range or more payload. But also that becomes a flight critical piece of the aircraft kit. If the tail rotor is lost, as is seen in every good or bad film in which a helicopter is shot down as the crew spin themselves wildly into the ground, there's no way to overcome that loss of a tail rotor. So the X2, with its counter-rotating coaxial rotors, solves for Mr. Newton's third law right there at the center of gravity, where your equal and opposite reaction happens directly over the top of the machine. So that frees you up to not have to have this tail rotor, and in fact, it allows you to have a thruster that is not a flight critical component, but one that you can switch on and off. The ability to switch it on and off, of course, provides you with an acoustic reduction as well as an ability to have it be more ballistically tolerant than its predecessor, the tail rotor. From an operational perspective, I would offer that the ability to change the pitch, both positive and negative, on the propeller has the advantage that you can use it both to accelerate, obviously, but you can also use it as a speed brake. So whether it's a rapid deceleration or the ability to prolong a dive, you can imagine the operational significance of those two maneuvers. So I think as we go into the future and the Army finds themselves hopefully in the possession of machines such as this, it'll offer them the opportunity to redefine the concept of operations that they bring to the modern battlefield and hopefully offer commanders more flexibility. Finally, I'd be remiss if I didn't close, having made such an issue of it earlier, that sustainment and maintainability are concepts that we try to incorporate into these designs. And when you look at the rigid rotor system, there's simply a parts reduction that you're able to design out of the main rotor system. And so immediately, with things like main rotor dampers no longer being critical to the blade dynamic, you've already dismissed one of your high, I suppose, cost and maintenance drivers. So with that, I will turn it over to my colleague and allow him to step through the rest. And Bill, just tell me when to hit the slide, and I'll do it.
Okay, Roger. Yeah, from paper to flight is a good thought that I suspect that most of the people attending this meeting are engineers that work on aircraft and people that work on aircraft. And it's amazing to go from an idea that somebody has that Sikorsky aircraft is going to go this X2 path. We're going to make these rigid coaxials with pusher props. And, when the Raider program started, it was, hey, what is our idea here? Are we do you want to sit next to the other pilot, or should you sit behind the other pilot? And you progress from there. You do this conceptual design review, preliminary design review, and finally CDR, and then you're starting to build the aircraft, and you see that aircraft come together. And so the part that Christiaan and I get to work on is really the fun part, right? Like the homework's mostly been done, and a lot of hard work, blood, sweat, and tears have gone into the machine before we ever put that thing in the air. So if you could go to the next slide, please. Mm-hmm. So here's a number of the elements that we have, and I'm going to talk to you about each one of these individually, but the operations analysis piece is one that I don't have a separate slide on, but that's kind of at the end of the day, what is this thing going to do for the customer? What is the customer going to do with this machine that they can't do with another machine? And if the answer answer is that they can't do anything with this machine, then you probably shouldn't be building it. And so you have to provide some additional capability to the customer. And so we look at that. We look at that in simulation. We look at that in the battle plans that our various military customers have. And what is the utility? How is it going to provide them an edge on the battlefield? And if it doesn't provide them the edge that they're looking for, then we're kind of iterative again, back to the drawing board to figure out how is it that we change the design to give them the capability that they're looking for. Next slide, please.
Coming. What's that?
All right, perfect. Yeah, so one of the bits of homework that we do is we need to figure out how this thing is going to fly and what are the loads, what are the aerodynamic efficiencies, and the asset out at Moffett Field in California, the National Full-Scale Aerodynamic Complex. We've put both the Raider and the Defiant models in there and run them through and collect all sorts of data on the aircraft. One of the difficulties with this asset is it's a fabulous tool to collect data, but a lot of people want to be able to use it. So what happens is you get a window and you have to have your model put together, the instrumentation all right, and start collecting data and being able to trend that data information and look at it. And you may not get as far as you want to get, and the people that run the wind tunnel are like, look, your time's up. We have other customers that are coming in here. And so then you have to pull all of your gear back out of the wind tunnel and beg them for another opportunity to come back and finish your work. But all of this information feeds into the aircraft design and the loads that we're expecting to see, and could result in changes to components that are already being assembled or just individual components that are being put together and built. Next slide, please. So ground test is one of my favorite parts of the test cycle of testing these aircraft, because we go through a rigorous ground test process at Sikorsky, where we've put thousands and millions of cycles on individual components. And you can look at some of these machines in the pictures here, and you know, there's not a machine for every component. And sometimes you're packaging a dozen different components into a single machine. And the way you stress those components in the machine here in ground test might not be the same way as you stress it in the aircraft in flight. And because of that and other reasons, you may break something in ground test, which is ideal in ground test. If you break something, then you've found the limit of that piece of equipment, and you know with relative certainty that how far you can push that component, and you know, of course, appropriate knockdowns on the ultimate loads on those pieces of equipment. But maybe because of the way the test is configured, you're not stressing the component that really is your limiting factor in flight test. And so now you're back to the drawing board and going back into ground test. And how is it that I stress the component that I'm seeing the highest load on in flight test that's limiting me? And the confidence factor for Christiaan and I is that all of these dynamic flight critical components are being monitored, and the engineers in the telemetry room are watching real-time loads on all of this equipment, and they're able to tell us, need you to back off, no more than what you have right now, or I need you to come home right now because you went over the limit. And so that's a lot of confidence. But it's also, like I said, if maybe you broke something in this piece of equipment that's testing a dozen different things, but what you broke isn't your limiting factor in flight test. So that's the iterative piece of flight test that can take more time than perhaps anybody would like it to take. But as good of modeling as we have, it's not perfect, and we're always going to find these sorts of issues as we go to flight test. Next slide, please. As pilots, a lot of our work homework in going to prepare for flight and to help evolve the aircraft is in our system integration labs. And these are up in Connecticut. And we have one for Raider, we have one for Defiant, we have one for all of the Sikorsky products that you're able to go in there and fly the aircraft. And you can see in here, we've got a nice big dome and a representative cockpit for the aircraft. Our fly-by-wire aircraft, we have the real flight control computers, the real hydraulic systems. We have the real engine control units. We don't have real engines, so we have a model that produces engine information to feed into the rest of the system. But we have real servos and swash plates, and then we have force generators that push against those servos and swash plates to represent or to replicate the loads that you see in flight. And so it gives you a high degree of fidelity. And we go through, and most of the time, what you see in the simulator is pretty close to what you see in flight test. And when we see something different in flight test that we didn't see in the simulator, well, then we go back and we reprogram the flight control software or the aircraft model so that the simulator is representative of the aircraft, and in order to go that next step to predict what we're going to see on the next flight as we expand the envelope, higher speed, more angle of bank, more load factor, whatever that might be for the next flight. We also have the motion-based simulator that's not depicted here, but sometimes it's good to have that feedback, that proprioceptive sense that you don't get in a non-motion simulator, that, hey, as helicopter pilots in the low-speed environment, you don't fly the attitude of the aircraft, that as you're hovering and the attitude has deviated, you're probably a step behind the aircraft at that point. So we get pretty good at sensing the accelerations of the aircraft and reacting before the aircraft moves anywhere. And so you don't get that out of these labs that don't move, because the visual sense is absolutely that. Your attitude has changed before you are visually able to see anything. And so sometimes it's good to get in the motion base and get that sense of acceleration that you have available there. Next slide, please. This is another great piece of equipment. So we take all of those dynamic components, the engine, the gearboxes, we string them together, and we bolt them to the earth, and we run it hard. And we run it hard and long to qualify the gearboxes, the rotor blades, those dynamic components. And just like the aircraft, this is highly instrumented, and we're sitting in a control room and watching all of this. On the Raider test stand, it was primarily all of the engineers were running this equipment and putting this through hundreds of hours of flight tests. And we found several issues here, a couple of which that could have been catastrophic on the aircraft. And so it's comforting to have this sort of equipment, this degree of fidelity in the aircraft or in the program, because you really bring the system out pretty hard and you work these components hard on this test stand. And now you're going to the aircraft with relatively pristine components because you have very little time on those components in the aircraft. So great piece of equipment. And next slide, please. You can just roll on one more. So just a side view of the Raider, 34-foot rotor diameter. It's roughly a 10,000-pound helicopter, and we go out and we fly. Most of our flights are anywhere from an hour to an hour and a half. Some of the goals down here at the bottom, 220 knots and 230 knots. We haven't quite got there yet. I think we underestimated the drag of the machine a little bit, and we've been over 200 knots, and I've got another point there where we get to that. But we have a 7-foot prop, 6 blades, and it's a single engine CT7-8 Alpha or YT706 of 2,600 horsepower, and retractable landing gear as well. Now, Christiaan talked a little bit about the tail rotor, so we don't have the tail rotor. We have differential torque between the main rotors to give us yaw control in low-speed flight, and then we have rudders for high-speed flight, and the flight control system automatically phases between the two. So as we accelerate out, it fades out the differential on the main rotors and fades in the rudder capability. Next slide, please. So the upper left, it says conventional transmission technology, and that's kind of the whole aircraft, really. It's conventional, like that in the sense that there's nothing new here. This is all components that are used in many other places, such that we've just packaged them in a unique way. But most of this stuff has pretty good maturity. So it's a GE YT706, so it's a variant of the T700 engine series that have millions of hours on it. It is a rigid rotor system, but there are plenty of rigid rotor systems out there flying. It's just that ours is considerably more rigid than some of the others, because to keep drag low, we keep those two rotor systems in close proximity to each other. We have a composite airframe on the aircraft. We also have UH-60 hydraulics and some of the electrical system. There's a cabin in this aircraft, and right now we have that mostly filled with instrumentation systems back there, but there's space for 6 people. We've had some pretty big Army guys back there with seats against the back wall and then backed up against the pilots as well, and knee space for their legs, that it can be quite roomy back there once you take the instrumentation stuff out. The original plan for Raider was to put a rocket pod and a gun on a podded gun on the outside of it, but we've evolved to our Raider X, our FARA offering, which has a different weapons package based off of the Army's requirements. The propulsor back here, I think Christiaan touched on it, that you have the ability to fly with or without that propulsor. The Raider aircraft, you can see the exhaust on the top back of the aircraft, and so that exhaust is really kind of blowing right through the prop. So when we disengage the prop to fly it in helicopter mode, the prop continues to turn. It's kind of a limited slip clutch back there, and it keeps the prop turning at on the order of 200 versus 2,000 RPM, so that you're not overheating the prop blades back there. The Defiant aircraft has a clutch capability on it as well, but it also has the capability to engage a brake on the prop, so we can stop it for ground operations. Next slide, please. So we set a pretty tall bar for some of the requirements of this aircraft. Now, this being a company-funded program, nobody was out there setting the requirements for us, and so we were trying to target what we thought the Army wanted out of the aircraft. And so 220 knots is the bar we set for the arms configuration, and so far we've been to 207 knots in level flight. We've been to 215 knots in a shallow dive. There is space in the back for those troops. I'm not sure what our status is right now with regard to hover performance. We set out to carry those troops and hover in 6K95 conditions, which is kind of the extreme of what the Army has been looking for. And the one performance target that is not on here, so there's 2 configurations for the aircraft. There's the armed configuration and there's the troop configuration. In the armed configuration, it's a little bit lighter machine than carrying basically 2,000 pounds worth of troops. And so the goal there was 10,000 feet at 95 degrees, and so that's pretty significant. And we did not reach that. But all I'd like to say is that by setting a high bar there, we've got a lot of margin. And as you have that high hot condition that you're able to achieve, and keep in mind, Christiaan said that the X2 tech demonstrator kind of started right after 9/11, a couple of years after 9/11, to where we're regularly fighting in the mountains of Afghanistan, where high and hot is a serious consideration for helicopters. So we didn't hit 10K 95, but we're trending closer to that, or we're above 6K 95 for that armed configuration. And so I think more capability than most helicopters out there. Next slide, please. Where we've been, so we're 90 flight hours on the S97 Raiders, and I told you about the speed. You know, the fly-by-wire is really a nice system. You can roll this thing over into a 60-degree angle of bank turn, let go of the stick, and hands off. It's holding that attitude until you tell it to do something else. And how do we control the prop? I don't think we've talked about that, have we? But there's a beeper on the collective. So grab the collective, beep the prop, beep forward to get more thrust on the prop, and beep aft for less thrust. So it's really quite easy, and you still have just the same controls you have in any other helicopter with a cyclic and a collective, and now you have this prop beeper. So we've done some 2G pull-ups, some 60-degree angle of bank turns, some side flight to 35 knots. It's pretty interesting to put some positive thrust on the prop and sit there in a hover, and we've hovered as much as, I think, just under 20 degrees nose up. The yaw rate at 30 degrees per second is just what we've programmed into the system. So it's step on the pedal, and if you put full pedal in, you're going to get 30 degrees per second of yaw rate. We could program that for more, but most of the time that's about all pilots kind of want in terms of that. We have a really nice ADS 33 course down in at Gwynn Field, and we recently, I won't say recently, it was about a year ago, I think, that we took, and myself and one of the other Raider pilots, we went out and we did some of the mission maneuvers. And it was interesting because the other guy that I flew with, it was his first time in the right seat of the Raider, and he went out, and most of the stuff he was scoring as level 1 handling qualities in the aircraft. And we are a rate command attitude hold aircraft with no airspeed hold, no position hold, no altitude hold. You know, those are all things that we've done on other aircraft and that we could easily do on this, but it wasn't really a goal of the program, and we didn't have a customer driving us to say, put all those bells and whistles in it, because I want to make sure that that you can do that. And so even without the pilot aids there, we're able to get basically level 1 handling qualities out of the machine. We've also done some acoustic testing. I was just looking at some of the record of that the other day, that we went 195 and 198 knot passes at treetop level to fly over the microphones. So that was some fairly fun testing to do. Next slide, please. In the future. So now Christiaan gets to start from blank piece of paper and work through the preliminary design review, the conceptual design review, and work our way through to Raider X, our FARA offering to the U.S. Army. I think is that it, Christiaan? The last slide.
It is. Yeah, that's the one.
All right. I think we probably have time for some questions if anybody has any.
Yeah, thanks, guys. That was really good. I appreciate it very much indeed. We've got 1 or 2 questions that have popped up. I'm going to try and experiment here, and I will unmute the person who's asking, let them ask the question, and then mute them again. Just kind of like some sort of debate I understand they're having soon. So the first one is from James Waltner. James, if you want to ask your question, you should be able to now, or maybe not. There we go.
Okay. I was wondering about the auto rotation. Does it auto rotate?
So we haven't done an auto rotation in the aircraft yet. We've gone full collective down. We've done some auto rotative rates of descent in the aircraft. We've done a lot of auto rotation work in the simulator, as you can understand, with kind of a one-off prototype aircraft, we don't necessarily want to put the aircraft through the risk of that touchdown auto at this point, but I think it's going to be coming up fairly soon that we'll do that. But in the simulator, it auto-rotates spectacularly if you've got the right energy state on the aircraft. That quite happy with the performance there.
Okay, John Dixon. Hopefully, if I get this right. Unless I get beaten by technology, stand by. John is self-muted, apparently. You there, John? There we go. Go ahead, John. We can't hear you.
That's okay, because I know John. That's John, a little scratchy.
All right, I'll ask his question. His first question is, what's the target roll rate at speeds above 100 knots?
So the flight control system has a programmed roll rate in there, and you know, right now we're in a competitive program with Bell for the Invictus, and you know, I think that it's high, but I'd rather not say right now in a public forum what that roll rate is.
Okay, well, John has a second question, as you might expect. Will the 97 or the Defiant be used to develop the maneuver envelope?
I think absolutely. I mean, these aircraft are tools to do some of that maneuvering, and you know, I mean, the first thing we're doing with the aircraft is we're understanding where all of the loads are and how we can get the weight out of the next aircraft. And so whatever maneuver envelope our FARA and FLRAA aircraft are going to have, we're going to want to inform those as best we can with these prototypes to make those aircraft as competitive as they can be. So yes, we are working on the maneuvering on these aircraft to the greatest extent we can.
Thank you. Anybody else got any questions? That's all I have right now. Either raise your hand or oh, Andy Bernhard's raised his hand. Go ahead, Andy.
Can you maybe explain from a pilot's perspective the difference in sensation between helicopter style takeoff, you know, where you push the cyclic forward versus a X2 style level takeoff and acceleration?
Go on,
sure. One thing to keep in mind is that a rotor is a spectacular acceleration device for helicopters. I mean, anybody that's ever flown John Dixon's probably got down to like an 11,000 pound Black Hawk back in the day, but even a 15,000 pound Black Hawk, when you shove the nose over on that thing and pull the collective up to your armpit and get 30 degrees of nose down, it accelerates like crazy. And so now you add to that this other dynamic of having this pusher prop. And so really we still use that main rotor because it takes a nice big bite of the air, and we use that for our acceleration, but we also feed in the prop. And so as you start getting some speed on the machine, that prop builds some efficiency and gets some airflow through it. And you can kind of feel it kick in. It's almost like a laggy turbo that prop gains some efficiency with every knot of airspeed. And as you're nose down accelerating with the rotor, it naturally gives you this cue that, uh-oh, yeah, now the prop's effective. And it just is a real natural cue that now I bring the nose up and I'm on the prop at this point. And the other feature with that is at that point, you're also hitting the speed where we automate the collective. So now the collective is automated by the flight controls and gives you the, puts the collective in the most efficient position for the speed that you're at the moment. And now you're just using prop for power, much like you're flying an airplane. The prop is probably much more effective as a parachute in the low speed environment where we're coming in to slow down. You really feel that thing kind of, grabs your shoulder harnesses, and that deceleration is just phenomenal. That number one, you're going from fast to slow very quickly. And number two, every other helicopter, when you come into that landing zone, now you're nose up and you can't see where you're going. So now, not only are you slowing down rapidly, but you can also see where you're going, because you can even do that a little bit nose down. Christiaan?
Yeah, I would offer to that too, that I think it adds for better speed stability, that the attitude is always pretty constant. And so I find that for just a rate command attitude hold system, the ability to target and maintain an airspeed in forward flight is quite a bit easier than I might have otherwise expected. We gave this talk out at the SETP conference, and one of our colleagues in Aero, I believe, described our ability to run downhill with the negative thrust on the prop and worry about decelerating too much as what did he call it, an inhuman act conducted in an orange flying suit. I think between that and the ability to position hold with the nose at these freakish attitudes without translating about is unique for sure.
Okay, I've got another hand raised. Carl Saul, I'm going to try and unmute you. Go ahead.
I have a question about performance. What is the specific range of an X2 technology aircraft compared to that of a conventional helicopter if they're operating at the same weight, altitude, and temperature?
Can you unmute Andy Bernhardt again?
Done.
You have reached Andy Bernhardt's voicemail.
I didn't realize there would be any math in the debate. Honestly, I would probably default to some of Bill's answer about the competition sensitive nature of performance data at this point. But what do you say, Bill?
I think if you look at, if we were to go back to the chart on the wind tunnel data, that the drag tends to be lower, and we're a little bit more efficient than a rotorcraft by, we have very low power on the rotor system. It's always driven, but the torques on the rotor system, you're using maybe 5% of your engine power on the rotor system, and the rest of it is just going straight into the propulsive capability of the pusher prop. The X2 Tech demonstrator saw efficiencies closer to a turboprop airplane than a helicopter. As we militarize and get more the Raider type design, we're somewhere in between the two, but I don't have the exact numbers for you.
Your question though does bring to mind a point that we hadn't really made, and I find it interesting, is that you almost reverse engineer these things maybe, in that you design the typical helicopter to just get off the ground with its maximum payload, confident that as you put the machine into forward flight, you'll gain efficiency and find yourself into the bucket. And for a true heavy lift machine, you could operate there until you'd burned enough fuel to begin to go faster. It turns out when you start going faster and faster yet, with velocity squared being a function of drag, that you actually have to spec the power for these things to meet the high speed requirement. And so that ends up providing you probably excess power in a lot of places that you might not otherwise find in a helicopter in the hover. Would you say that's fair, Bill?
Yeah, absolutely. That's how we're able to get those, 10K 95 type numbers as a target, because you've got that power available already for pushing you through the air at your airspeed target.
I got time. I think we got time for one more question, and it's probably the one you've been waiting for. And this is from Kevin Quach. Go ahead, Kevin. Okay, well, he's having some difficulties, so I'll read it to you. What's the biggest advantage of X2 technology versus the tilt rotor?
I think it's the ability to decelerate rapidly. that it's kind of a combination that we're able to decelerate rapidly, and it's also the footprint of the aircraft, that it's a nice compact tight footprint of the aircraft that you're able to get into a tight landing zone. So when you're flying a tilt rotor, you have nacelles when you're going fast that are down in airplane mode, and you have transition windows that you have to have a certain speed in order to get those nacelles to that halfway point, and then another speed to get them all the way up, and then to put those back. And that takes time. It's configurable. And the other thing is they're pretty slick aircraft as well. And so when you pull the power back, it doesn't want to slow down until you're able to get those nacelles up and in order to slow the thing down. Whereas our aircraft, you're able to just start taking the thrust out of the prop, and really when we move the prop back just a little bit, you immediately feel that sense of deceleration. And so kind of a metric that's kind of ballpark is 200 knots to a hover in just over a half a mile, where if you're 200 knots in a tilt rotor, you're probably like 2 miles, that if you're not configuring at that point, you are way behind the power curve. It may be more than that. So I think it's the ability to keep the heat on until the last minute, particularly when you're going someplace to land where people might be shooting at you and you want to be less vulnerable. Christiaan?
Yeah, I would have said that the requirement to sort of transform, if you will, to change your capability. I think the ability to clutch up a prop and change the pitch on it without any drastic, I don't know, change to the plan form of the machine is pretty slick. But.
Okay, well, I think that's it. I want to thank you again, gentlemen. There was a comment from Mr. Dixon just congratulating you on the work you're doing, and I think we all echo that. And I'd like to thank all of the people who attended tonight. We got 43 people in all come. So thank you very much. This was a good first successful attempt at our audio meetings, and let's do some more. Thanks again, guys, for doing that. We really appreciate it.
Yeah,
Hey,
well,
thanks
what
for
a
coming,
pleasure.
everybody.
Yeah, thanks.